So we have another section over properties. This one is properties of natural logarithms where x is a real number and x is greater than 0. So when it comes to natural logarithms, we have the notation of ln. Again, this is ln, not in, So ln. The reason I write like this is because this is what you will see on a calculator. So let's talk about it. Our first property is ln of 1 equal to 0. Now, I want to talk about ln. The notation of ln is the same form as log with a base of e. So, when you have ln of 1, so ln of 1, it basically means log base e of the 1 power. So when you have that, now if ln of 1 equal to 0, therefore log base e of 1 equal to 0. So again, ln, the notation is short for log base e. So when you have ln of 1 equals to log base e of 1, so if I were to write that in exponential form, then basically it's e to the 0 power equal to 1. And e is also the function, just like log and natural log, or ln, on the calculator. There's a button for e, there's a button for log, and there's a button for ln. So all of these are functions that has a close relationship to each other. So again, anything powered by 0 is 1. So that's why ln of 1, which is the answer, equals to the exponent, 0. So this is always true. Now again, this one is for that. Now if we were to talk about this, ln, or natural log of e, if I were to convert that to logs, so from natural log to logs, it's log base e of e, and it's equal to 1. So if I were to convert that into exponential form, I use the base e, whatever it equals to, as the exponent. So e to the 1 power is just simply e. So anything powered by 1 is itself. So again, I converted natural log ln into log base e, and then I have e right here in parentheses equal to 1. So from there, if I convert it into exponential form, I use the base e to the power of 1. So anything times itself, to the power of 1, is itself, which is right here. So let me make a little mark. This e is from that e right there. So tying to natural log, so whenever you have ln of e, it's just simply equal to 1. That's why. So when you have ln next to e, it always equals to 1. And then here I just prove why it is true. Now moving on to the third property. When you have ln of e to the x power, it will always equal to x. So, for example, if you have ln of e to the 5th power, it always equals to 5. If you have ln of e to the 25th power, it will equal to 25. So maybe ln of e to the 31st power, then it will equal to 31. And then let me prove that, why it works. So again, ln of e to the x power, you can rewrite it as log base e of e to the x power equal to x. And again, I use this x from here. So again, if I were to write that as exponential form, So I have my base e with my exponents here equal to whatever in here, e to the x. Well, then we can see that e to the x equals to e to the x. So the left side equals to the right side, and the right side equals to the left side. So that's true. So that's why this right here is pretty much the same as common logarithms. And then here, when you have ln of e to the x, it's just simply the exponent. That's all it is. Now the last one. These two ties in together. Now when you have e to the power of ln of x equal to x, so it's pretty much the same as this one right here. So when you have e to the power of ln of x, it's just simply whatever inside the parenthesis or what's next to ln, which is x. So for example, like say we have e to the power of ln of, say, 71. Then 70 is just going to equal to 71. Now if it was, say, e to the power of ln of, say, y, then it's just going to equal to y. That's all it is. So all you have to do is just memorize that. When you see e next to the power of ln, then it's just simply what's inside of ln is the answer. Alright, let's do some basic examples. Evaluating with natural logarithms, or ln. So if we have, on our first example, ln of e to the power of 1.5, if we use the properties of natural logarithms, then whenever ln is next to the e, then whatever the exponent for e is always the answer. So it's just going to be 1.5. So that's our answer. Simple as that. And let me box that up for y'all. Alright. So again, whenever we have ln of e to the power of 1.5, or say 2.6, it'd be 2.6. It was ln of e to, say, 3.7, then it'd just be 3.7. Now over here, in our second example, ln of 32. Well, there's no way to work this out by hand, so this one, you actually have to use a calculator. So what you have to do is just type in exactly what you have, ln parenthesis 32 close parenthesis. And then when you type it in and hit enter, the answer will give you approximately 3.47. So whenever you see something like this, ln of 32, you would type it into the calculator, and then this would be your answer. Or whenever you have a problem, and then when you simplify it, if you get down to natural log or ln of 32, the only thing you could do is plug into the calculator to get your answer, or if it asks you to simplify, you would stop there. Okay, so for example 3, we have a natural log of -5. Well, if we tie back to where natural log is the same as logarithms, the properties are consistent. In the properties, we know is that whatever is inside the parenthesis, it wasn't 0 nor negative. It was always just positive numbers. So if it was positive number, we can work with that. In this case, it is not. So again, logarithms, same thing as natural logs, it cannot work with 0 nor negative numbers. So whenever you see ln of -5, then simply you would see it equal to a 0 with a slash, meaning an empty set, 0 slanted. So that means that it's basically undefined. That's what the answer is going to be if you have a natural log or just log with a negative number inside the parenthesis. then it's just going to be undefined. So in example 4, we have something the same. It's natural log of -6. So if it's just a negative number, then yeah, you can write it as undefined. In some cases, the answer would be just a symbol with a circle and a slash. Now again, you can write that if it was just a negative number inside a parenthesis. But if it has a variable, say -6x or -5 plus x, then yeah, you can keep working with that and find out what x is. So if whatever x is make the number inside positive, then yes, you can work with that. But whatever x is and it makes it negative, then it's automatically undefined. So again, with logs and natural logarithms, if it has a negative number and just a negative number, it's always going to be undefined. Alright, now we have more examples working with natural logs, including the e function. Alright, so in this example, e to the natural log of 6. So based on the properties is whenever e is raised to the power of ln, whatever is inside the parenthesis is just the answer. So e to the power of ln of 6 is just simply 6. That's it. Now, in this example, e to the ln of 3x, so it's pretty much the same property as before. So whenever e is raised to the power of ln, whatever inside the parenthesis is just the answer. So in this case, we have 3x, a number with a variable. So all we have to do is just write 3x. And then that's our answer for these two examples. So again, there's nothing you could do with this 6, so you're done right here. There's nothing you could do with the 3x, so you just leave it as b. And then you're done with those two examples. Alright, now, in this example, ln of 1 over e to the 4th power. Well, in this case, we do have a fraction. So, what we can do is, using the exponent laws, we can convert this from a fraction into where e to the 4th power is in the numerator. So if I were to rewrite it where we don't have a fraction anymore, it would be ln of, since it's e to the 4th power, I just convert this to e to the negative 4th power. That's it. So 1 over e to the 4 is the same as e to the negative 4th power. So whenever you have ln next to e, then simply the exponent for e is the answer, so negative 4. Now, it's okay to have a negative exponent for e, but when you have ln, whatever inside the parenthesis, if it's a negative number, so if e to the negative 4 was equal to a negative number, then it would be undefined. But in this case, e to the negative 4 power, negative 4 is the exponent, so that's okay, which is why we can have it equal to a negative number. So just to review, when ln of a negative number is undefined, but it is okay if e, the function, is powered by negative 4. Now over here, it's the same process as that, it's a fraction. So if I want to get rid of the fraction, meaning move the e to the x power to the numerator, then I rewrite it as, and then here's why I keep saying e to the x power to the numerator. If I bring it to the numerator, it would be e to negative x over 1. So this is why I said that you bring the e to the x from the denominator to the numerator. Again, I did not switch, I just simply moved it to the numerator. So 1 over e to the x power is the same as e to the negative x over 1. So basically, e to the negative x over 1 is just e to the negative x. Whatever divided by negative by positive 1 is just by itself. And then when ln is next to the e, then whatever your exponent for e is the answer, so negative x. So following the properties of natural logarithms, whenever natural log or ln is next to e, then whatever exponent for e is, that's the answer. Same here. So again, to review, I did not switch their places. I simply moved e to the x power to the numerator by changing the exponent, which is x, to negative. Now, whenever you have a number besides 1, it stays where it is. So for example, if we had, say, 3 over e to the x, and well, let's say it's 4 on the bottom too. So if I want to move e to the x to the numerator, so all I have to do is convert the exponent into its opposite sign, so which is negative. So I'm going to move e to the x to the numerator, and when I do that, I convert it into a negative exponent for e, so negative x, and then the 4 stays where it is. So again, that's what I mean by moving the e function with the negative exponents to the numerator. So when I have like e to the 4th, I simply move it to the numerator. Same thing here, e to the x, I simply move it to the numerator. Anything that's already there besides 1, like such as 3, you see how 3 stays in the numerator, and then 4, it stayed where it was, which was in the denominator. So again, I did not switch places. I just simply move e to the x to the numerator and change the exponent to negative. That's all I did.